trying to get good at figuring out which test to use. So the best thing about this section is that there's just random series and you're trying to figure out cold, which one do I use? When you're in the ratio test section, guess which test you use. When you're in the root test section, guess what test you use. But here, we were trying to sort of do it from scratch. And that's a hard thing. And so it's a really good section if you want extra practice with the test. Going to chapter 10, section 8 in the study plan, you can really try to hone your skills at trying to analyze whether it is geometric, whether it's a p-series, whether it's a ratio test, whether it's a root test, all those things. So when we look at this one, the first thing that we want to keep in mind is that when we have a k power, like if we look at the geometric series, we have a r to the k. That exponent is just a k. In none of the forms of any of our series do we ever have, like a k plus 4 or a 2k, things like that. So if we see a modified k in the exponent, the first thing we should say to ourselves is, let's rewrite that so that we have just a k in the exponent, because then it's going to be much more recognizable. So when we look at this one, in order to change that exponent so that it's just a k, we're going to use our laws of exponents. If we have 3 to the k plus 4, that's the same as 3 to the k times 3 to the 4. So we can break that exponent apart and get to where we need to be. So this is going to be 3 raised to the 4th power multiplied by 3 raised to the kth power. And down below, this is going to be 5 to the k. I'm going to put the constant out in front, and 5 to the negative 2. And the series starts at 0. So is that okay with everybody? Do you see how we can do that constant manipulation with the laws of exponents? All right, well, let's then pull our constants out to the front. We know that we can factor constants out to the front. We know that constants multiplied by series don't change convergence or divergence. So when we pull the 3 to the 4th out, that's going to be pulled out as an 81. And this in the denominator, that's a 5 to the negative 2. So that's a 1/25th in the denominator. So if we move it up to the numerator, then it becomes a 25. And what we have remaining in our summand is that over that. They both have a power of k, so we can unite them. And this can be united into a 3/5 raised to the k power. And now that we've done all this algebraic manipulation, now we can really look at it and identify it as geometric. So that is definitely geometric. And you will indicate to me that you know it's geometric by identifying R. And so will this one converge or diverge? Converge. So this R value, we compare it to 1, it's less than 1, so therefore we have convergence. And on the exam, every geometric series that you encounter, you'll be asked to find the sum of the series. So if we want to find the sum of this geometric series, we're going to have this 81 times 25 out in front. All right, that's just a constant multiplied by the geometric series part of the expression. And we know for the geometric series, if we want to get the sum of this entire series, we also need to know the a value. The a value is the very first term in the series, which will be
3/5.
1.
Okay, 0.
So we look at that initial, if it started at 1, then yes, it would be a 3/5. But because it starts at 0,
It starts at 1 so often.
it starts at 1 so often that that's easy to make that mistake. And if it started at 2, the first term, the a term, would be 9/25.
Yes.
So whatever that initial index value is, that's what we have to go with. So then our formula for S for a geometric series is a over 1 minus r. So we come over here, so our S, we've got these two constants in front that have to be multiplied through. And then we multiply that by a, which is 1 over 1 minus r, so 1 minus 3/5. So we're going to have 81 times 25 times, this is 2/5 in the bottom, which is 5/2 if you flip it over. So we just have to simplify that. So whatever all that is, 125 times 81.
1,100 or 10,125
There we go.
over 2.
So that'll be the sum of our series. Yeah, so recognizing geometrics, as soon as you see a power of k up in that exponent position, you should be thinking, is it geometric? There's k up there. All right, when we look at this one, what kind of series is that?
Geometric.
That is geometric. It's in the exponential form. Geometric has an exponential form, right? The exponent is where the k is. It's where the variable is. And the base is a constant. All right, does this one, so we identify it as geometric. I know you know that because you're going to write r equals that. And does this converge or diverge?
Diverge.
So we look at the value of that, and the value of that is bigger than 1 because the numerator is about 3.7. The denominator is about 3.1, so that's definitely bigger than 1. And then our conclusion is therefore it's going to diverge. So a couple of geometric series. Any questions on either of those before we jump to the next couple?
Will we have to specify if it's positive or negative infinity, or just therefore diverge?
Diverge is enough. Yeah, diverge is enough. Most of the time we're dealing with positive numbers, so if it diverges, it's going to go to plus infinity.
Or if it's an alternating series, you go to both.
It diverges to both.
Well, I guess the values diverge to both, but the sum diverges to one.
All right, how about this one? So first off, we see that sine function in the numerator, and we have seen some alternating series that have a sine or a cosine being implemented as a switch. Is this sine switching?
No.
No. Certainly there are negative values. Like if we look at sine of 3 or sine of 4 radians, that would be a negative value. But it's not alternating. There's like some pluses and then some minuses and then some pluses, and so it's just sort of random.
Because you're adding 5 to it too.
And
It
then
will
we're-
always be positive.
So this value is not oscillating. It's just randomly going up and down between negatives and positives. And on top of that, we're adding 5, which is always bigger than the most negative it ever could be. So the numerator is always positive. Okay, so we've got that going for us. Now, we have a denominator that's a square root of k, which reminds us of which series? A p series. A p series is where k is in the base and the exponent is constant. So the exponent is a half here. So we've got those two different cases. We've got the geometric where the exponent is where the k is. And if we have the p series, it's 1 over k to the p. So it's down here where the variable is. So for a p series, the variable is acting more like a polynomial. For a geometric series, it's acting more like an exponential. All right, so that looks like a p series, but it's not a p series because the form of a p series is 1 over k to the p. So if we have a series that's like a geometric but not, or like a p series but not, which test do we go with? Comparison. Because we know how to analyze a geometric series very easily with the a and the r. We know how to analyze a p series very easily with the p. If we have a series that's just a little bit tweaked, then we go with the comparison test. And so we're going to choose our b sub k in a way that we are basically ignoring the insignificant terms. And when we look at that numerator, okay, the numerator is not constant, but it is bounded by a constant, right? This numerator is never more than 6. It's never less than 4, right? Because sine of k is wobbling between -1 and 1. So the whole numerator is wobbling between 4 and 6. So it's not a constant, but it's kind of constant-like. So if we got rid of that numerator, we could have this. So our first choice in our mind would be, let's just compare it to that. And we know that this p-series does what?
Sorry.
This would diverge, right? This we would say, oh, p is 1/2, and 1/2 is less than 1, so therefore we would have diverge. Now let's think about the inequality. If this p-series diverges, we suspect that this one diverges, and we know that bigger than diverging diverges. So could we show that this one is bigger than that one?
Yes.
Yeah, we could. All right, let's confirm it. Maybe it's not obvious to you, but let's see if we can do it. If you're looking at it trying to develop a hunch, this one would be bigger than this one because its numerator is bigger than that numerator. 5/2 is bigger than 2/2. So if the numerators are bigger and the denominators are the same. So in this case, we would want to show that our a sub k is bigger than our b sub k because the b sub k that we chose led to diverging. If we want to show that that's diverging, this is the direction we would need to show. So we're going to have 5 plus sine of k divided by root k. Is that greater than 1/root k? Multiply both sides by root k. So we're going to have 5 plus sine of k greater than question mark 1. Subtract 5 to get -4. And that's a true statement. We can solve that by inspection. This is true. This is true. Right, sine of k is always greater than or equal to -1. Doesn't matter what the k is. So this is true. So therefore, both series will diverge. Since our comparison series diverges and we showed that this one is bigger, it must also diverge. So therefore, both diverge. Logically make sense? Bigger than diverging diverges? Thanks. Smaller than converging converges. Those are our two basic principles. Now let's take a look at this one. This one, same idea. We have a numerator that's wobbling between, in this case, 2 and 4. Right? Cosine of, who cares what the angle is? Biggest it is 1, smallest it is -1, so it's wobbling between -1 and 1. So the numerator is wobbling between 2 and 4. Same idea. Okay, that wobbling is kind of acting like a constant if the denominator is getting enormous. So our first instinct would be to go comparison with 1/k cubed. We at least would start with that. We would identify p as 3. This is bigger than 1, which tells us that we have convergence. Now, we can go through the inequality thing here, but let's think ahead. Let's think, this is what we would want to show. We would want to show that a sub k is less than b sub k, because smaller than converging would converge. Will we be able to show that here? No, we can't show that here. Because if we think ahead, if we were trying to show that this a sub k is smaller than this b sub k, it's not true, because this numerator is bigger than that numerator. So here's where we have to be clever. We could say, oh, it fails, let's go to the limit comparison test. We could do that, that's totally fine. But we could also say, well, this is a p-series that converges, and if we multiply it by a constant, it's still going to converge. We could just pick this numerator in a way that is bigger than that numerator. We'd still have convergence, right? So if we, what constant do you want to pick?
10.
10. So if we pick 10 and we factor that 10 out to the front, that still converges. 10 times a convergent p-series still converges. And if we do that, then our a sub k is going to have a numerator that's smaller than the numerator of the b sub k. So this is what we would want to show. And it doesn't matter what this constant is as long as it's bigger than 4.
We put those 10s in red, or just a different color. So
Yeah, absolutely.
doing homework.
So and again, the 10 is just random. You could pick 6, you could pick 7.
Yeah.
You could pick anything. So we want to pick something so that this numerator is larger than that numerator. The numerator on the left is never bigger than 4, so if we pick 5 or more, it's going to be fine. It could be, you could pick 2 pi if you wanted, but we'll just pick a constant because an integer constant, because that's just easy. So the k cubes, these cancel, right? If you multiply both sides by k cubed, those are positive numbers. You can multiply by positives and not worry about the inequality direction. So those just cancel. And if we subtract off the 3, we have an inequality that we can solve by inspection. This is always true, right? Cosine's never more than 1, so this is true. So therefore, both series do the same thing. So since we chose a b sub k series that converged, the a sub k series must also converge. Now, if you didn't see that right away, if you didn't see this sort of clever manipulation with the 10, we could just go with limit comparison test now. So if we wanted to, we could go with limit comparison test, and let's just see if it works out easily or not. So the limit comparison test would say, well, let's take the limit of a sub k over the b sub k. If you can't get the inequality to work how you want it to, let's go with a limit. The limit kind of washes out some of these little inconsistencies with the inequality constants. So here we would do the limit of a sub k is that. And if you divide by b sub k, you're multiplying by the reciprocal of b sub k, so we would get this. And then this is the limit, the k cubes obviously cancel. And oh gosh, you come down here, and the limit comparison test says if the limit exists and is a positive real, both series do the same thing. This limit, as k goes to infinity, does it exist? No. This limit does not exist. So that tells us that this is an example where the limit comparison test is actually inconclusive. And so we actually do need to know how that direct comparison test manipulation works, because most of the problems we've seen, if the direct comparison test didn't work, the limit comparison test would. So this is an example, a counterexample of where the limit comparison test doesn't always work. So this means that the limit comparison test is inconclusive.
So let's say on a test we're moving through, we don't get the comparison test, we go to the limit comparison test, and therefore we get doesn't exist for the limit.
Yeah.
Do you recommend going back?
Then we go back and we
mess
fiddle
it?
with our b sub k.
Okay.
We go back to b sub k and massage it.
Will either one work all the time? Things like one.
In
or
this
the other?
class, so I will tell you on the exam what test to use. I'll say use the comparison test. And so one of them, the comparison or the limit comparison, will work. Yeah. It's possible to create a series where although I don't know an example off the top of my head, where the comparison test will fail in both cases. But that just means another test would work. There's like natural tests to choose. Factorials, choose the ratio test. Probably don't want to use a comparison test with factorials or power towers and things. But usually comparison is when it's p-series-ish or geometric series-ish, the last slide. Yeah, those are the two that we usually go. Because you need a B sub k that you can get your hands on really easily. You got, and geometric and P are the two that, oh, it converges, R is less than 1. Oh, it converges, P is bigger than 1. So those are the ones that we usually are going to go comparison on. All right, what test jumps out at you here? The root test. Because we see a power of k on the outside, and the root test immediately gets rid of that power of k so that you're analyzing whatever the base is. So that's a pretty obvious one. So we're going to use the root test and hope that it gets us where we need to go. So we're going to take the limit as k goes to infinity of the kth root of the absolute value of a sub k. So that's the root test, kth root of the absolute value. We don't need the absolute value here because there are no negatives in that summand, nor will there ever be any negatives. So we can actually just eliminate that absolute value thing right away. So we're taking the kth root of all of this, k to the k and k plus 2 to the k. So that just wipes out that exponent, and we're just analyzing the base. So we have that. That limit is 1. And what does the root test say if we get a 1?
Want the inconclusive one?
Yeah. So root and ratio, if we get a 1, it's inconclusive. That means pick a different test. Like, oh, crud. All right. Let's look at this. What about when we look at this summand? If we look at it like this. Remember that we should always think about the divergence test, at least loosely. Is the limit of a sub k 0? If the limit of a sub k is 0, then the divergence test is inconclusive and we have to do something else anyway. When we look at this, what form, if we take the limit of this,
Oh, it's the.
it's a 1 to the infinity. Isn't that an indeterminate form? So 1 to the infinity. 1 to the infinity is our classic indeterminate form that leads us to E. All right, the 1 to the infinity indeterminate form are the breadcrumbs that tend to take us to modifications of the exponential. So let's see if we can do this without using the log limit thing. Now on the exam, there will be a question that says use log limit, so you need to know how to use log limit. But if we wanted to go with the shortcut would be, well, the denominator here has 2 terms. That's not something that we can break apart. So let's flip it. So if we flip the base, what do we have to do to the exponent?
Negative.
Make it a negative k, exactly. And now we can break this base apart so that we have 1 plus 2 over k to the minus k. And what does this go to as k goes to infinity? E to the negative 2. So remember that our generic is that if we have the limit as k goes to infinity of 1 plus a over k to the bk, that's going to go to e to the product of a and b.
Can you show like how to do the root limit,
Yeah, log limit.
log
Yeah.
limit?
Yeah,
to know how to do
definitely. So what is our conclusion here?
No.
So this is, yes, what's the conclusion?
Yeah. Not equal to 0. divergence.
So therefore diverge. So this is diverging by the divergence test. So if that limit's not 0, there's no way the series converges. Because in the tail, it's like adding e to the negative 2 plus e to the negative 2 plus e to the negative 2 forever. Right? For the rest of eternity, that cannot converge. All right, so let's do one where we do the log limit process. So if we do the log limit process, we are thinking about, usually we convert this over to x's because we know we're going to need a derivative, and generally k's are discrete and x's are continuous. So we create a function, a continuous function. We take the log of both sides. So we have the log of y, and on the right, when we take the log, the whole point of taking the log is that the exponent can jump out in front. We can get it out of the exponent position. And then we take the limit of both sides. And on the left-hand side, when we take the limit, we move it inside the log, foreshadowing in the end that you have to exponentiate to get the limit isolated. And so on the right-hand side, when we take the limit, oh, and this should be an x, since we switched over to x's. And what we're trying to generate on this right-hand side is something that will be in L'Hopital's form. And so the way that we typically have done it is by shoving one of the functions into the denominator. And 99% of the time, the function you shove into the denominator is that multiplicative function in front of the log. And if you move something into the denominator, it turns into its reciprocal. Multiplying by x is the same thing as dividing by 1 over x. Multiplying by 2 is the same thing as dividing by a half. If you divide by a half, that's multiplying by 2. If you divide by 1 over x, you're multiplying by x. And that puts us in L'Hopital land. Right, so this is, as x goes to infinity, we end up with a 0 up top and a 0 down below. So now we can use L'Hopital. As soon as we get that indeterminate form, L'Hopital comes into play. And so, let's see, let's go down here. So we'll rewrite it down here. So we're going to take the derivative up top, derivative down below. We still have the limit as x goes to infinity. Okay, derivative, let's do the denominator first. That's always easier. That's x to the negative 1, so it's negative x to the negative 2. Negative x to the negative 2, we could rewrite like that. In the numerator, derivative of a log, first step is to flip the guts. Reciprocal of the inside. So reciprocal of the inside, first step. Multiplied by the derivative of the inside. And the inside is a quotient, so we have to use the quotient rule. So we do low d high. So low, the derivative of the numerator is 1. So low d high minus the numerator, which is x. The derivative of the denominator is 1, all divided by the denominator squared.
You did the numerator squared.
Say again?
You did the numerator squared?
I did?
No, it's
So
Denominator.
this fraction right
Oh.
here, so the low is the x
I
plus
thought you were
2.
copying it from the bottom. You're copying it from the original natural log?
From right here, yes.
Yeah, okay, got it.
Yeah. Oh, I see what you're saying. Not from here.
Yeah, okay.
Yeah, from here. So the derivative of this piece right here is low d high, so low is the x plus 2, d high minus high is that high, d low is that over that low squared. Yeah. So from the original. And that takes us to, let's just write it all out in longhand. So this is x plus 2 over x. This, we're dividing by 1 over x squared. So that means we just flip it and multiply. Doesn't matter really where we put it. We'll put it at the end. So then up here, notice that in this numerator, this is just x plus 2 minus x. X plus 2 minus x, what does that turn into? 2. So that's 2 divided by x plus 2 squared. And then we flip this thing and we get negative x squared over 1. And now we just have to simplify all that. And that's not too hard because we have a lot of cancellation. Let's see, so we end up with limit of one of the x plus 2's cancels, one of the x's cancel. So I'm seeing negative 2x over x plus 2.
Yes.
And what does that all equal? The limit of that as x goes to infinity. -2, because we have polynomials with the same power, so we take the quotient of leading coefficients. Or you could divide each term by x if you wanted. So now we're down to the limit is -2. So if we look at the left side of the equation right here, there's the left side, and here's the right side. And that tells us that the limit of y, if we exponentiate both sides, the limit of y is e to the -2, which is what we got above. So then we make our conclusion that this is not equal to 0, therefore diverge by the divergence test. I end up with the same answer. Of course. You should end up with the same answer. Who would hope? If you don't, back to the drawing board. But when you see those powers of k out there, supernatural instinct is let's try the root test. Because if the root test works, the root test is fast. Didn't work in that case. So we're in a very similar boat here. Power of k on the outside, let's go root. Makes perfect sense to give that a quick shot because it is so quick. So if we take the limit kth root, absolute value, a sub k, as k goes to infinity, I think we can probably take the kth root of all that in our head. So we end up with 2 times 3 over k. So this limit as k goes to infinity is 0, which is less than 1. Oops, is that our conclusion? Do we go less than 1? For root and ratio?
Greater?
Yeah.
No.
It's,
Do we compare it to 1 for root and ratio?
yes,
Yes,
because it's.
because it's the geometric series cousin. So therefore converge. So the root and the ratio are cousins of the geometric series. Our
Which is
conclusions
less.
are the same. Less than 1, converge, greater than 1, diverge.
Series is the other way.
P series is the other way around. P series is the one series where it's reversed. Yeah, so if the root test works, it's usually, child's play, normally. But you do have to make sure that you're good on the conclusion. Root and ratio, cousins of the geometric series. Less than 1 converge, greater than 1 diverge.
Now on the test, you're gonna say use the root test, so we don't have to put root test is for the convergence.
Therefore, by converge by root test?
Yeah.
Yeah, no, you don't have to put that.
Okay.
Because I am telling you which test to use. Yeah. Yeah,
Okay.
yeah, that's a good question.
And if you tell us which test to use, you don't want us to use other tests, like just.
Yes, exactly.
Grab.
Yeah,
divergence
don't
test
just
and
randomly grab, I mean, you can for fun,
Yeah.
and see if you get the same answer.
It still should solve.
Yeah,
Whatever.
if it says use the ratio test, that's what you should use.
Even if it would be easier to just diverge.
Even if it would be easier if it was the divergence test.
Dang it.
Series.
All right, how about this thing?
Divergence test?
Okay. So the divergence test says if the limit is not 0, it diverges.
Oh, wait, but it doesn't.
What is the limit of that?
It doesn't work for this one.
What's the limit of that?
0.
0, yeah. Limit of that is 0.
Yep.
Because as k goes to infinity, the limit can jump inside of sine because sine is a continuous function. And as k goes to infinity, the fraction goes to 0, but sine of 0 is 0.
Dang it. You're
So
right.
the divergence test, good first thing to look at, is inconclusive. Okay. Now, there is a very clever, and this was, well, I shouldn't say was, but it should have been pointed out to you long ago. But even if it was, I'm sure you forgot it. So let's take a look at something that's super interesting. And it becomes important, it was important in Calc 1. And we're going to see it again actually today when we look at Taylor polynomials. Let me just draw this angle here. So here's theta. Theta is that angle. And you know a relationship between r theta and S. S is the arc length. What is that relationship between theta, r, and S? You remember?
For very small theta.
No, for all
Oh,
theta.
for all theta, it's, yeah, r theta. I was thinking of, it's very close to sine for small
Yes.
theta.
So that's what we're going to look at in a moment. So for all, this is always true. S equals r theta. You know, sometimes if you can't remember it, what sometimes is said is that if you look at theta,
Only one radian though.
you could say that theta is S over r. It's almost like slope. It's almost like slope because that's also a representation of r right there. It's like arc over, you know, instead of rise over run, it's like arc over run. So it is a lot like slope. Okay, so that is true. And if we were, I heard someone say unit circle. So if we were on the unit circle, so if r equals 1, then S is equal to theta.
Your arc length is your radius.
So the arc length and your angle have the same measure. Obviously, arc length is measured with units of length, and the angle is measured with units, quote unquote, of radians. But they have the same magnitude. The arc and the angle are the same. S equals theta. You know, it's very similar to what we talked about with when we were doing those rectangles and height. If you look at this and say the height of that is 4, well, you could also create a rectangle that has area 4. So here we have distance of 4, here we have area of 4. It's just they have different units, but they have the same magnitudes. Same idea. So furthermore, when theta is small, if we drew a picture of what sine of theta is this distance right here. It's that vertical distance. Ooh. It's that vertical distance right there. Everyone agree with that? That that's sine of theta? All right, sine of theta is right here. And theta and S are the same, so there's theta right there. That's a terrible little arc. So you can think that as, why am I not red anymore? So if you look at this picture here, if your theta is small, sine of theta and theta, because theta is the same as S, they're about the same. So for small theta, sine of theta and theta are about the same. Okay? So if you look over here, when k is getting large, that's representing 1 over, that's the angle theta is 1 over k to the 9th. So as k is getting bigger, that angle is small. So sine of small angle should be closely approximated by the small angle. So the small angle is 1 over k to the 9, which leads us to the comparison test. So this leads us to the comparison test, and we would choose for our b sub k to be that small angle, and that small angle in this case is 1 over k to the 9th. So that's going to be our strategy. What kind of series is that? P series. So P is equal to 9, which is greater than 1. So therefore we have convergence. So that's a convergent P series. Those summand values go to 0 really fast. 1 over k to the 9 goes to 0 really fast. So it's going to converge. Okay, so we suspect that this converges then. Let's see if we can get to our want to show inequality. So we would want to show smaller than converging converges. So we would want, oh, let me use the, usually I put the generics first. So we would want to show that A sub k is smaller than B sub k. That's what we would like to show. Okay, so then we want to show that sine of 1 over k to the 9 is smaller than 1 over k to the 9. That's what we want to show. Now, this can be shown, it's kind of this is one of those subtlety things where a lot of times we just do this by inspection. If you look at this picture, sine of theta is right there, and theta is right there. You can see that sine of theta is smaller visually in that picture than theta, right? Because theta and s are the same. You could also, you could do some other things too that are more technical, but this is really from Calc 1, this is an accepted fact that sine of theta is less than theta. So this is already known to be true. So there's a couple of other technical ways you could show it, but if we just look at that picture, it's pretty obvious that sine of theta is the vertical distance, theta is the arc. That's true. So therefore, we have both series converge. Both are going to converge. You could also look at something like if you look in Desmos, let's go to a new Desmos thing here. If you look at Desmos, if you graph y equals x, and you graph y equals sine of x, you can see, let's just try to stretch this out a little bit. Stretch that direction, stretch this direction. And you can see that sine, the blue one is sine of x, the other one is x. Right? You can see that as you zoom in, there's always going to be a gap between them. As long as you're to the right of the y-axis, as long as you're a little bit over here, the red one, which is y equals x, is always a little bit tiny bigger than sine. So that, so you can look at it, you can show it geometrically that that's going to be true.
And also, that picture shows a great reason why, when it's small, it's basically the same.
Basically the same.
Basically the same.
And we're going to see that really soon when we look at Taylor polynomials, which are extensions of the tangent line, that sine of x and x are about the same when x is small. Okay, so that is going to converge using the comparison test there. Okay, how about this thing? So with this thing, again, we see that power of k on the outside, so our gut is let's probably go with the root test. That's probably where we think to go first, so let's quickly do a root thing just to see if we can get there. I thought I had another pen. I must have left it over there somewhere. So root test, we would take the limit of the kth root of a sub k as k goes to infinity. So kth root, absolute value of a sub k. Absolute value is not going to matter here because everything is positive. So the kth root is really a power of 1 over k. So we take negative k squared and multiply by 1 over k, and it eliminates one of the k's. So we're going to, kth root's going to wipe out one of those k's, so we're going to have k over k plus 10, all raised to the negative k. Now, this is another one of those 1 to the infinity indeterminate forms. In this case, once again, we can't split this fraction because there's 2 terms in the denominator. But if we take that minus and stick it down below, that's going to change the numerator and denominator. It's going to flip it. It's going to take the reciprocal. So we get that. Now, the inside can be split into our classic form. And that limit, e to the 10. Okay, so root test. We end up with a constant that is greater than 1. So our conclusion is divergence. It's cousin of the geometric series. Less than 1 converge, greater than 1 diverge. So this is greater than 1, so therefore diverge.
And on the test, that's all you want to see is right there?
Mm-hmm.
Okay.
Yep. That's all. Yep. That shows you everything right there. So root test worked out great there. And normally, again, if the root test works, it works really fast usually.
And what is it? It's e to the a times b. What is it again?
Yeah. So it is that right there. So 1 plus a over k to the bk will go e to the ab. So that's the first question on your worksheet, is to work out that math. All right, so the worksheet is due soon,
1 week.
in 1 week from today. And that is the first question right there. You know, do the log limit process to show that that's e to the ab.
That shouldn't have worked.
What's that?
Nothing.
Nothing.
Dumb thing.
Dumb things are happening? Okay, so, all right, that's chapter 10.
Yeah.
Now, if you look in most calc books, they combine infinite series with power series. It's one big chapter. This book is the first book I've seen that actually separates it. They do the chapter 10 is the infinite series of numbers. And then now we'll go to chapter 11, which is an infinite series of functions. In particular, an infinite series of powers of x. So now we're not looking at random infinite series like Fourier series where you have an infinite series of sines and cosines, which you will get to. We are going to be looking at infinite series of powers of k, hence power series. Power series meaning a series of powers of x. So here is what a power series looks like. So a power series is just an infinite polynomial. Maybe it's better to say a never-ending polynomial. But a lot of times we'll just use that word infinite for things that just go on forever. So there is a power series. Power series is a function. You can plug in any number you want for that x. Right? Sounds like a pain in the neck to calculate. If you were to plug in -3 or +3 or -0.1 or +0.1 or pi, you would have this infinite summation, which is chapter 10. We would have to figure out, does it converge or diverge? All right, so for a power series, some of the x's that you might put in could converge, some could diverge. Okay. So if we just imagine this as, if let's just suppose all of the constants were 1. So let's just suppose all the constants were 1. We would have this. And what kind of series is that? What'd you say?
I want to say geometric.
Geometric. Geometric. Because we are doing constant multiplication by x. So that is geometric. And we know that geometric series converge if
X would be less than a half.
x
Or
would
less
be
than 1, sorry.
less than a half.
Less than a half. I don't know where I got that.
We've not- half.
I have no idea what that means.
Why? So if the magnitude of x, because x could be positive or negative, this will converge if that's less than 1. That will give us converge. Otherwise, diverge. Right? But now, when you look at that, you are imagining throwing in every possible x. It's now a function. It's not just, so every value of x leads to its own infinite series. So when we imagine a power series, you're imagining, like a pincushion with all these infinite series coming off of it. Some of them are going to converge, some of them are going to diverge. If you plug in a 2, it diverges. If you plug in a half, it converges. If you plug in a 0.9, it converges. If you plug in a 1.1, it diverges. Right? So you're imagining this horrible visualization where there's an infinite collection of infinite series. And the ones that have an x value between -1 and 1 will converge, and the other ones all diverge. Okay, so that's what a power series is. A power series is this function. Sometimes it converges, sometimes it diverges. And what we will end up doing is, whenever we talk about a function, we think about the word, what's the first word when someone says function? You start thinking about the domain, like where is the function defined? Where is the function undefined? Like that becomes a very natural question. And with a power series, the idea is that the x's for which you get convergence are where we would think of it as being defined. And the x's for which you get divergence, we think of that as sort of being not in the domain. So the domain values for a power series are the x's that give you a convergent series. So we would kind of think of the domain of this power series right here as -1 to 1. Now they don't use the word domain with a power series, they're going to use the term interval of convergence. And so, oh, and that should be an equal, not a element, but an equal. So the interval of convergence is the analog to the domain. It tells us the x values for which the function, in this case, that geometric series, is convergent. All right. Now, power series can be centered at the origin, or they could be centered somewhere else. So up here, you're imagining all those x's as x minus 0, x minus 0, x minus 0. So that center is 0. If you wanted to shift something left or right, you would put an A right there. If A is positive, what direction is this being shifted? To the right. And remember, like x minus 2 is shifted to the right 2 units. If you have y equals x minus 2, you shift it to the right. X plus 2, you actually shift it to the left, right? The shift is always the opposite of what you see. So if A is positive, this would be shifted to the right. If A is negative, it would be shifted to the left. And we call A the center of the power series. So the center is A. Most of the power series we see are going to be centered at 0, but not all of them. Okay, so that's the basic definition of a power series. Never-ending polynomial.
And will they always start with k equals 0, or is that variable?
Hello, Aaron.
Jim, how are you doing?
I'm doing well. So this is Aaron. He works down in the Academic Success Center, and he is going to talk to you all for about 5 minutes about being an SIL.
Well, thank you.
Where he is.
Can you guys all see me okay over here? Because I can be Mo. Okay.
Wherever you want to be.
Awesome. So guys, I want to be very respectful of your time, but I also want to,
Power series, the one that you probably will see the most as an engineer will be the exponential. So here, and we'll talk about how you build these power series, but at this point we're just sort of saying, these power series are infinite polynomials. So that is the power series for the exponential function. We call this over here the expanded form with the dots. So that's expanded, and then this is the summation notation. And for the exponential function, the interval of convergence is all reals. So it doesn't matter what real you plug in, you're going to get a convergent series of numbers on the right-hand side. Which is not surprising because you see that factorial growing in the denominator, and we know that factorials dominate polynomials. So that numerator is polynomial in nature, the denominator is factorial, so it's going to take over, and it doesn't matter what x you plug in, x equals 50 billion, it'll converge. So e to the x, that's its power series. Natural log of x, another common function. Here is its power series. Notice that the exponential one is centered at 0 up here. This one down here is centered at 1. And also notice the difference in the domains, or the difference in the intervals of convergence. That one, all reals, that's only defined for 0 to 2. So it's much more restrictive. We'll talk about why that one's only defined from 0 to 2. But one thing that we're going to notice is that these x values, it may not seem obvious at first, it might feel like the x's could be scattered, the ones that converge. But it turns out they're going to be clumped together. If you have x's that converge, they're always going to be in an interval, and you will always have divergence outside of the interval of convergence, which is interesting because there's times where you look and you're thinking, oh, well, and this one's going to be a good example. We'll look at a little bit about why that is. Okay, so this takes us back to Calc 1 and the tangent line. So hopefully you found the process of finding the equation of the tangent line pretty straightforward, because we're going to up the ante dramatically here. The tangent line is just the best linear approximation. We are going to be talking about the best quadratic approximation, the best cubic approximation, the best quartic approximation, the best quintic approximation. You can extrapolate from the tangent line and get a whole sequence of approximations that get better and better. Let's go to Desmos for a second. So if you look at, here's the black curve right there is e to the x. That purple curve is the best linear approximation, which is the best first order approximation, and this is all centered at the origin. So that's the best linear approximation right there. And you can see, yeah, if you go, over to 0.5 in each direction, it's a pretty good approximation. Well, if we jack this up by 1, now we've got the best quadratic approximation at 0, and you can see that there's an even deeper overlap with the original function. And then we can go to the best cubic approximation, and the overlap is going to get better and better, and you can keep on trucking. These are called Taylor polynomials. And if you look, the right-hand side matches really well. The left-hand side, we've got to, if we want to get matching out here at -10, we just have to go further and further out, blah, blah, blah. But it will eventually match. And so what I have here is the Taylor polynomial of degree n. And the farthest I went out was 20, but you could obviously keep on going. Let's look at another function. So let's take off e to the x. Here's the arctangent function. Let's go back. So there's the arctangent function in black. And if I go to 1, that looks like crap. Oh, that's the wrong. Here's the one. So that one's the tangent line here. So let me get to 0. So when n is 0, when n is 0, we're going to have power of 1 on x. So that's the tangent line. So this is similar to sine of x in that sine of x and x we saw earlier are approximated by each other when x is small. Similarly for arctan. Arctan of x and x are about the same if you're near the origin. So it's similar to sine x and x. And same idea. There's the best now there's not even powers for the inverse tangent Taylor polynomials. If you look at that exponent, it's always going to be odd, right? Plug in a 1, plug in a 2, plug in a 3. It's always odd. So there's the best approximation that is going to have, what is the power of that thing? When n is 1, that's a power of 3. So that's the best cubic approximation, then this is the best quintic approximation, etc. So same idea. But what we notice here is that there is definitely a range. It is not getting closer in either direction. And we'll have to figure out what those values are. It's pretty, what do you think they are?
1 and -1.
1 and -1 looks pretty good. We'll talk about why those are. It's very interesting though, because isn't that arctangent function, it's continuous everywhere, it's differentiable everywhere. It is one of the better behaving functions because there's no points of non-differentiability. So it feels like, well, why the heck isn't there a Taylor polynomial that can go as far out as you want? That's a question. Like with this next one, it's a little more obvious. So when we look at this reciprocal function here, there's the first order Taylor polynomial at 0. i.e. the tangent line. Like with this one, you see this asymptote right there, right? At x equals 1. So it's not surprising here that as we go, the interval of convergence is actually going to be -1 to 1. It's not surprising because we have an asymptote 1 unit away. But what's really mysterious is that you would think that we would be able to build polynomials that would start matching out here. But there's some inherent quality to the Taylor polynomial that picks up the fact that there's an asymptote 1 unit away, which will not allow convergence beyond 1 unit in the opposite direction. So if you're looking at trying to build these Taylor polynomials, if you're 4 units from the nearest asymptote, that's going to be your radius of convergence. Your whole interval would be 8 units long. So it's really interesting that somehow it's built into the process of building these Taylor polynomials that you have this, wherever the closest asymptote is, that dictates the width of the interval.
Is that a good reason to choose a different center point
Yes.
for your thing? So you could choose to center it at like -5.
100%. So if you were curious about numbers between -4 and 5, you would center it somewhere over there so you don't have to go as far out in the series, and so that you can get to the point you want to get to. Like if you're curious about stuff right here, you would want to shift that over so that it's centered close to where you're interested. And then similar, so there's 2 reasons to shift it off of 0. 1, so that you have convergence near where you want to be, and 2, you don't have to go as far out in the series to get accuracy. You don't have to go out to like 1,000 terms. You might only need to go out to 20 terms if you shift it. So both of those things are reasons. Okay, so we're going to look at the mechanics of building we're going to build the quadratic. So you know how to do the tangent line already. That's old hat, theoretically. So this is the equation of the tangent line. And in this class, because we are building an infinite number of them, we're not just going to call it L, because there's an infinite number of polynomials. So P sub 1 will be the first order Taylor polynomial. P sub 2 will be the second order Taylor polynomial. P sub 3, the third order, etc. So the tangent line has that form. And what we want to notice with the tangent line, 2 things. Value and slope match the original function. So the original function is called f, and the tangent line has these 2 properties. The tangent line is good because A, it matches the value, so the value is that dot right there, and it matches the slope. So now that begs the question, well wait, what's the slope of a curve? By definition, the slope of a curve is the slope of the corresponding tangent line. So if someone says, what's the slope of this curve at a point? It is the slope of the tangent line. So the curve and the slope and the value match. Now, is there any question on this right here, as that being the equation of the tangent line? So the point right here on the graph, the point of tangency is a comma f of a. Is that okay? And the slope of that tangent line is f prime at a. At the point of tangency, the slope is the derivative evaluated at the x value. And then you just do point slope formula. All right, you do x minus a, y minus f of a, and then you solve for y, which we're calling p sub 1. So that is the equation of the tangent line, point slope formula. Do we need to go through it, or is that clear? If we did y minus f of a equals the slope times x minus a, and then we add the f of a to the other side. That's supposed to be just a plus. So we add the f of a to the right-hand side. Oh, come on. And then we're going to call it p sub 1. So that's the tangent line. Okay? So now if we want to build up and get to a p sub 2, the best quadratic approximation to the function, so that's the thing in blue, we are going to have a third match. So for p sub 2 to be the best quadratic approximation, we certainly want the values to match. So the quadratic better have the same value as the original function. We want the slopes to match, and we want the concavity to match. So we're going to keep ratcheting out further and further. And we have names for these, the best value, the value, the slope, the concavity. Once we get the third and fourth and fifth derivatives, we just say that they match. We don't have a specific word that we necessarily use. So if we want to build the best parabolic approximation, the best quadratic approximation, we start with the tangent line. All right, there's the tangent line. But then we need a quadratic term, and we have these three things in mind. So we've got our tangent line. We want to add a quadratic term. If we want the values to match, that means when we plug in an a for the x, we need to get a 0 here, because the f of a is the value, right? F of a is the value right there. That's the value of the original function, the black function up there. That's f of a. So when we plug in an a here, this term disappears and this term has to disappear if we want to enforce that the values match. So this quadratic term has to have an x minus a in it so that this will cancel out when we plug in an a. Now, so the C2 is what we're trying to find. If this is going to be our quadratic term, we don't know what the coefficient should be yet, but we know that we know that it has to have an x minus a squared. So now let's take a derivative. So we know that we want three things to match: value, slope, and concavity. We want those to match. So we're taking our p sub 2 right here, and our goal is, well, how do we find the c sub 2? If we know c sub 2, then we know the form of the quadratic approximation. Just like, right there, we know the form of the linear approximation. Right? We know that the coefficient, right, this coefficient right here in front of the x minus a, we know that that's f prime of a. Now we need to do a similar thing. We need to find this. What is that one equal to? All right, so that's what we're going to do. So we're going to take our general form of p sub 2, and we want to find what C2 has to be to create this best quadratic approximation. So first I'm going to take the derivative. So I take the derivative of p sub 2. On the right, what's the derivative of f of a?
0.
0. It's a constant. F of a is the value of the function. It's a number. So its derivative is 0. How about the derivative of this piece right here? F prime of a. Because if we come out here, if you were to distribute, f prime of a is a number, right? It's the slope of the original function at a. And if you distribute that f prime of a, you would have this. All right, just distributing f prime of a. This whole thing is a constant. F prime of a times a is a constant, so its derivative is 0. This is linear. The derivative of a linear expression is just the slope. It's the number in front of the x. So the derivative of this middle term here is just f prime of a. Now we go to the last term here. The derivative of that, we use the chain rule. So the 2 is going to come down, the power rule part of it. The 2 is going to come down, and we subtract 1 from the exponent. All right, so 2 down, subtract 1. And then what's the derivative of the base?
0 minus 1.
Close.
Or 1 minus
1 minus 0.
Yeah.
The derivative of the base, derivative of x is 1, derivative of a is 0, 1 minus 0 is 1, so multiplying by 1, we don't have to show it. So that is the first derivative of p sub 2. Notice that if we replace the x's with a, we're finding slope. So if we put an a in right there, p sub 2 prime of a, that's the slope. And if we plug in an a there, it goes away. So far, we've now shown that p sub 2 matches in value, because if we plug in an a up there, we get just this. And now down here, the first derivative is slope. If we plug in an a here, we get just that. So we now have it matching in value, matching in slope. Now let's take the derivative again. Derivative of the left is just p double prime. Oh, f prime of a is a constant, so its derivative is 0. And then how about the derivative of this piece right here?
Constant times.
2c sub 2.
2c sub 2, right? Because if we were to expand this, this is 2c sub 2x minus 2c sub 2, geez, times a.
Constant.
And this part right here is a constant, right? That is constant, so its derivative is 0. So we end up with just 2c sub 2. And now we have that, we can isolate the c sub 2. So now we have that, oh, c sub 2 is the second derivative divided by 2, and if we were trying to find the approximation at a, we're going to plug in an a right there, and that gives us our coefficient right there. Second derivative of the original function at a divided by 2. So we now know that the first coefficient is the first derivative at a. The second coefficient is the second derivative at a divided by 2. What do you think the third coefficient might be?
Third derivative divided by 3.
Super close.
Third derivative
By 6.
divided by the factorial?
Yeah, exactly.
6.
Super close. So if we went out and we were to do the same thing where we match value, slope, concavity, and whatever we call the next one, jerk, whatever you want to call it, you would see that you would end up with a third derivative at a divided by 6. And not just 3. It feels like it should be 3 when you look just here, but obviously you need to go further out in the pattern. And if we do the extrapolation further out, oh, I didn't write it. If we do the extrapolate, it's coming on the future slide. So if we did one more term, we would end up actually with this. And so the denominator, you can think of this as a 1 factorial here. You can actually think of this as a 0 factorial here, because 0 factorial by definition is 1. And then this you're going to think of as 2 factorial, and this one will be 3 factorial. So that generalization for that leading coefficient will always be a factorial, which we will see on this slide here. So here is the general form of the coefficients. It's the kth derivative evaluated at a divided by k factorial. Okay, but we'll get to that in a minute. So let's focus on these linear and quadratic approximations. So here we're going to find both the linear, the quadratic, and then we're going to do an approximation of the given expression that they have there. So I find it really easy to do these if you stay very organized. And what I will do is approach all of these approximation ones by, I'll usually switch to y because it's usually easier than the f stuff. So I'm going to start with the function, and I'm going to just come down here and take derivatives. And we need to get to the second order approximation. So if we want to get to the second order approximation, we're going to need down through derivative 2. So first column is the original function and its derivatives as far as you need to go. If we wanted to get to the fourth order Taylor polynomial, we'd have to go to the fourth derivative. So if we're just going to the quadratic approximation, we just have to get to the second derivative. And then we want to evaluate each of these at the center. So y of 1, y prime of 1, y double prime of 1. So we've got our original function and its derivatives, and then we have the function and its derivatives evaluated at the center. So they have to tell us the center. So they tell us we're going to center these approximations at an a value of 1. Now we can build. So p sub 1 of x, it's a function. This is the tangent line. And usually that's a little p. That looks like a large p. It's Usually we just use a small p. So p sub 1 of x is going to be value, right there, value plus slope multiplied by x minus the center. And usually we don't simplify these. Usually we'll just write them like that. Obviously you could simplify, you could distribute this minus and write it as 2 minus x. Usually we don't do that because we want to see the pattern. We don't have to do that step. Usually we want to see the powers kind of separated out, parsed apart. So there's our tangent line. And then our second order approximation is the tangent line. So there's the tangent line part. Now we need the coefficient of the quadratic part. So the quadratic part is going to be an x minus 1 squared. And we have to deal with the coefficient. So the coefficient is the second derivative, right there, divided by 2 factorial. Just like the coefficient of the linear term was the first derivative divided by 1 factorial. Next coefficient, second derivative divided by 2 factorial. And again, usually, and that should be an equal sign right there. Sometimes we simplify the coefficients, sometimes we don't. It depends on the problem. Most of the time we don't require the coefficients to be simplified, most of the time. So that is the second order approximation. Now it says evaluate. So we want to figure out, we want to approximate. So P1 of, let's see, so x is the denominator. This denominator is 1.05. So if we want to find an approximation for P, or if we want to find an approximation for this fraction, 1 divided by 1.05, what that means is you want to plug in 1.05 in for x, right? And so our approximation, our linear approximation, might be easiest to actually look at the simplified form that we don't usually go to. So 2 minus 1.05, what, 0.95? And if we do p sub 2 at that x value, we plug in, you could take, this is the linear one right there, so you already have that value, 0.95, and then we're going to add 0.95 minus 1 is 0.05. It doesn't matter that it's plus or minus because we're going to square it. So 0.05 squared, everyone agree with that? And then plug that into your calculator, or whatever we get. Someone plug it in. So 0.95 plus 0.05 squared. What do you get for that whole thing?
So 0.9525.
Oh, it is that simple. Okay. Oh yeah, so that's going to move the decimal to
2 spaces.
Yeah, gotcha.
It's just hundredths to thousands, which is
So there's our approximation. And somebody else type into the calculator 1 divided by 1.05. What do we get when we type that in? So 0.95,
238.
238, etc. So the tangent line, actually, all we did was go out to the tangent line, and it's good to 2 decimals, which is, these Taylor approximations get better quite fast usually. This one is good out to 3 decimal places already.
we're also only 0.05
Away from the point of tangency.
So it's
That's,
going to be pretty close.
it's going to be pretty close, yeah.
Just because the equation's not that messed up that over
And which sort of
very small.
tells us why we want to get the center close to where we are interested.
Because if we put in 0, I'm sure it would be
Yeah, then we'd have to go further out.
approximation for first.
Correct. So let's do this one. We're going to start at y equals root x. So I'm going to write that. So start with the function. in a form that's easy to differentiate it, so we're going to make that a power of a half. And then we do, if we're only going out to the best quadratic approximation, all we have to do is get down to the second derivative. So first we do that, column of function and derivatives. And then we evaluate at our center. Center is 4. So y of 4 is 2. Y prime of 4 is 1/4. Y double prime of 4 is negative, plug in a 4 there, square root of 4 is 2. 2 to the negative 3 is negative, no, 2 to the negative 3 is 1/8. So it looks like to me 1/32 with a negative. All right, any question up to that? Yeah,
How do we know to only do a quadratic or whatever?
it was just in the instructions.
Okay.
Yeah, it just said do first order and second order.
Would they go to word problems on these, like say find the jerk or something?
Mm-hmm.
Or find the snap or whatever?
Yeah, whatever they're called.
Okay.
In math books, they won't call them anything. They'll say find piece of 4, find piece of 5. So what is piece of 1 of x then? So that's the tangent line. Tangent line is value plus slope multiplied by shifted x. There's our tangent line. Value plus slope times shifted x. And that's it. Piece of 2 is tangent line. So we rewrite the tangent line. And as you do more and more of these, you start to just sort of build piece of 2 and identify piece of 1 as part of piece of 2. There's shortcuts. But there's piece of 2 with the tangent line. Now to get the concavity part of it, we take the next derivative, so minus 1/32 divided by 2 factorial times shifted x squared. And normally we will, do some simplification of coefficients, not necessarily all the time. Here it's simple enough to just simplify that second coefficient since we're simplifying just one coefficient. All right, so there is the best linear approximation. There is the best quadratic approximation. And here, they're saying approximate the square root of 3.9. All right, with the center of 4, so obviously we're trying to choose as our center the perfect square that's closest. You could pick 4, you could pick 5, you could pick 1, but 4 is going to be the square that's the perfect square that's closest to that one. So if we want P1 of 3.9, I guess I can do it there. So piece of 1 of 3.9, so the tangent line approximation, that's going to be 2 plus 1/4 times 3.9 minus 4, so negative 1/10. And then we're going to type that into our calculator and get something.
79/40 or
79/40, because that's 1/10, so that's going to be
1/40.
80/40 minus 1/40. Okay, yep. And then this one will be the tangent line approximation, which is 79/40. And now we just need that last term, so it's going to be minus 1/64 multiplied by, once again, if we do that, that's going to be 1/10. Squared is 100th. And what do we get when we do that? What does that turn into as a fraction?
Well, I don't know, it's a fraction, but it's 1.97515625.
And what is this one as a decimal?
1.975.
And, let's see, so the original was square root, so what about square root of 3.9? What do you get when you put that in?
I have the fractions. 12639 over 6/400.
And 1.9748. So very close.
Yeah, so super close. And that's the type of stuff you'll do in numerical analysis classes where you've got some infinite series and you want to approximate. So a Taylor polynomial is just the beginning of an infinite series. An infinite series, we are going to see a power series is going to be created from these Taylor polynomials. So obviously you can imagine going further. If you go on forever, you've created a power series. So right now these are called Taylor polynomials because they're polynomials. But all you have to do, if you did this, if you went plus dot dot dot, now it's power series. Right? Now it goes on forever. Now it's power series. So so Taylor polynomials are Taylor polynomials are one type of power series. And so what's going to be interesting when we go back to here and look at that e to the x thing, where was that? Back here? Where was it?
Probably the first slide.
Oh, was it that far back? What did I just do?
11.1. You added a page.
Did I add a page in
Or
there?
maybe you moved forward.
Or moved a page?
You
At least I just undid it. Wherever that e to the x thing is, there. So this power series, notice that it's equal to e. So if you take this process, if you construct a power series by doing what we just did, so that's a constructive process. We do that repeated differentiation, build all those coefficients. That's how this polynomial is built, this power series. It's built by taking e to the x, taking repeated derivatives and building that. And there's a little justification that needs to be made for them to actually be equal to each other, right? Because the Taylor polynomials are approximating, but then if you go on forever, it turns out that it is actually equal to the function that you started with. And there's a little bit of math there, a little bit of analysis that takes place in a couple of courses above calculus. Because if you think in your mind, any function that you can differentiate, you can build the power series for it. But that doesn't necessarily mean that it's going to be equal to the function that you started with. Right? So if I give you a differentiable function, you start taking derivatives, you can build a power series. That doesn't prove that it's equal to the original function.
And it's also only equal within that range.
Within that interval of
Interval of
convergence.
convergence?
Yeah.
Gotcha. Which is why ln of x centered at 1 is only true for 1 degree to each side.
Yeah.
Because that's when you hit the asymptote.
Yep. Exactly. So if we wanted a larger interval of convergence here, if we wanted to get an interval of convergence that's larger, we just shift it further away. So if we did x minus 3 instead of x minus 1, the interval would be from 0 to 6. Because 3 units would be the distance to that vertical asymptote for natural log of x. If we shifted 3 to the right, we would have 3 on the right of that and 3 to the left of that. We get an interval of like 6.
Gotcha.
All right, so we're building quadratic approximations.
Finish that.
So in general, a Taylor polynomial, so here they talk about the general form of P sub n, and it's just what you think it would be. So we did the value, we did the slope, we did the concavity, and if we keep going where all the derivatives match, P sub n, the last term of it would be the nth derivative evaluated at a times x minus a to the n. So that's how you would generalize what we just did for quadratics. And big key right here is that the coefficients are just these derivatives evaluated at the center divided by the power factorial. So Taylor polynomials generalize the concept of linear and quadratic approximations. So here again is e to the x. P sub 1 is the linear approximation, P sub 2 is the quadratic approximation, P sub 3 is the cubic approximation. Just gets better and better the further you go out in the derivative train.
And P sub 0 is just the value.
P sub 0 is just the value.
P sub 0 is just what is it equal to at that point. Okay.
So here we want to say, we want to find P1 through P5 for that function centered at the 0, centered at the origin. So e to the negative x, exponential decay. So you want to build a very systematic way to do these things. So again, I think it's easiest to use a y, f prime of x. It just gets very kind of overblown and messy. It's just easier if you use y's. So now we need to get all the way down to how many derivatives? To the 5th derivative. So we're just going to keep on trucking with our derivatives first. Oh, that becomes a plus. And then the 3rd derivative becomes, oh, that's a minus up there. I'm losing minuses left and right. And once we get past the 3rd derivative, that's where we start using the numerical thing up in the parentheses.
And so parentheses means that it's the derivative instead of.
Parentheses means it's a derivative instead of a power, right? All right, so there we go. Function and derivatives all the way down to the 5th derivative. So that's what we need in order to build P sub 5. And then we go ahead and evaluate at the center. They said center was 0, so y of 0 is 1. Y prime of 0 looks like negative 1. Y double prime of 0, positive 1. Y triple prime of 0, negative 1. So you can see that we're getting an alternating series. All right, so there are the derivative values at the center that we chose, or they gave to us. And now it's going to be a pain in the neck to build P sub 1, P sub 2, P sub 3, P sub 4, P sub 5. So usually what I do to shortcut that is just build P sub 5 and then identify the other parts of it. So P sub 5, we start with the tangent line. That's value minus slope times shifted x. Oh, no shift. No shift. It's centered at 0. So we don't have to shift the x. So there's the tangent line. There's P sub 1. Now we go to concavity. There's concavity divided by 2 factorial times x to whatever the power is. Don't have to shift the x. Now we go to cubic. So it's minus 1 divided by 3 factorial. And then it's not a shifted x, it's just an x because our center is 0. It's going to be x cubed. Okay, and now we go to the 4th derivative. 1 divided by 4 factorial, x to the 5th, minus, oops, that's an x to the 4th. Minus 1 over 5 factorial, x to the 5th. That thing right there is going to be a 4 if I can get rid of it. Yeah, that scribbly thing doesn't work great. So there is your 5th order Taylor approximation. And if they asked for all those other things, this right here is P sub 1. It's built right in. So doing it like this is totally sufficient. P sub 3 is going to be out to there. P sub 4 would be there. So if you just build the one that has the highest order, the other ones are just subsets.
And that presentation is fine, we don't need to write them out.
Totally fine by me.
Fine in future classes too, usually.
Usually, yeah, usually. All right, why don't you all try one? Try this one for cosine. So find, and I hear they're nice. They're just saying find p sub 4 and p sub 5. So find p sub 4 and p sub, basically go to p sub 5. And here the center is going to be pi divided by 6. So build that Taylor polynomial, fifth order. And you're going to see that sometimes, depending on the center, you're going to get zeros, especially with sines and cosines. So your fifth order polynomial might actually only be a fourth order polynomial. You know, if there's a term that's missing. Now that's not going to be the case here because pi over 6 doesn't give any zeros. But you'll see that they're, like we saw with that inverse tangent one, there were some powers missing. The nice thing about these polynomials, it's very procedural and it's very repeatable. You do it a few times and it's all of a sudden, it's like, okay.
Yeah, except for when you're doing fractions on
Except
top of factorials,
fractions on top of factorials can complicate things.
Yeah.
and your calculator doesn't do it.
Your calculator will do it.
Not giving you a fraction, they'll give you a decimal.
Oh, yeah, depends on how big it gets.
Yeah, how big it gets.
Yeah.
And the homework doesn't like decimals.
No, decimals suck. Because you never know with the decimal. With the fraction, you know it's exact. With the decimal, you don't know. You know, like if you stop at 5 decimal places, it's unclear. There's no notation that indicates that's exact. That's why we prefer fractions unless necessary.
Pi over 3 is
Pi over 6. Which is root 3 on 2.
too much physics.
I did the same thing.
Don't be in degrees. Any questions on the derivatives? That all match everybody's expectation?
Yes.
And then y. So then we're just going to plug in this pi over 6 all the way down. And obviously you're going to have a lot of repeated values. We're dealing with a periodic function. Oh, sine of pi over 6, 1/2.
So then
Just imagine failing a math test because the odd year on the. Just imagine if you were to fail a math test because you're in calculators and degrees and radians.
Don't do
I
it.
don't need to imagine.
I've
Don't do it.
I've done it.
Yeah, right, you don't have to.
I've done it. I don't
Yeah.
have to imagine.
What was that Mars rover called? The one that they blew up because they forgot to convert to meters instead of feet? Which one was that one?
Centered on.
No, it's not the challenge.
What a horrible mistake. Oops. Surface is coming faster than expected. Mayday. Is anybody in here watching that new Netflix series, The Three Body Problem? No one watching that yet? Just came out on Netflix. It's some 8-part series. You know, The Three Body Problem, where you get 3 like things moving around in space trying to figure out the pattern that they're gonna do. I just watched first episode last night. It's pretty freaky so far. All right, so to build P sub 5, we're going to start with the tangent line. So we start with value. Come on. Value, slope, multiplied by shifted x. So there's the tangent line. Value minus slope times shifted x. And then we go to concavity. And we get to Bryce's favorite part, fraction on top of a factorial.
Yeah, it's great fun when you get down to 5.
And yeah, right? It's just gonna get better. So there's the best quadratic approximation, aka P sub 2. And then we go to P sub 3, I'll put it down here.
Yeah.
So to get to P sub 3, we're gonna have plus 1/2 divided by 3 factorial, since we've got the third order derivative. Then we have our shifted x raised to the third power. And then plus root 3 divided by 2, all divided by 4 factorial, x minus pi over 6 to the 4th. And our last one, minus 1/2. And so you do not need to go through, like on a test, you could just leave it like this. Simplifying all these coefficients is just busy work, not necessary.
So we can leave it that way?
Yeah, absolutely. You can leave it that way. What do you say about the calculator is?
That's what my calculator's for.
Yeah, exactly.
Will MyLab Math accept it like that?
It actually should.
Okay.
Because it's usually set to accept all numerically equivalent answers.
So where's the factorial? Is there a factorial button?
If there's not, you can try.
You can just use the exclamation point. It'll do it as a
It's the
factorial.
same thing as factorial.
Yeah.
And it should be analyzed the same. There might be a button somewhere in the file.
So if we were trying to talk about just P sub 4, I think it's obvious that P sub 4 just stops at the 4th order term. That would be P sub 4.
Turn it into an oblique.
Would you accept it written vertically if we made it like a table that was just like next to the value so we don't get ourselves confused? Like have it as root 3 on 2 and then the line below it minus, so having it written.
So having it like this, just
vertically.
written.
Yeah.
Yeah, that's fine.
Cool,
Be
'cause
fine.
then
Yeah.
my brain just forgets which line I'm on.
Yeah,
So
well,
I'm
yeah.
like, am I on the 1/2 term or the 3/2?
Yeah, this is more like accounting than,
Yeah.
just trying to keep track of where everything goes.
Yeah.
Yeah, that would be totally fine.
I do it vertically, then they're all just next to the term that they're related to, which
Yeah,
is
that's-
really straightforward.
Totally fine. Okay, so here it says, approximate the given quantity using Taylor polynomials with n equal 3. Compute the absolute error in the approximation, assuming the exact value is given by a calculator.
It doesn't give us a center point then?
Well, we have to figure that out.
Gotcha.
So when we look at this number there is, obviously we're using a tangent function. And so we would want to pick a center that's super close to negative 0.1, so we'll choose 0.
Gotcha.
So we're going to start with y equals tangent of x. And it said n equals 3, so that's third order. That doesn't mean 3 terms, right? It means third derivative. So that's usually 4 terms. So then we're going to get down to our third derivative. Derivative of tangent is secant squared. Yeah, this can get messy fast when you're dealing with trig functions. So derivative here, we do the power rule first, 2 secant of x to the 1 times the derivative of secant, which is secant x tangent x. So we're going to get 2 secant squared times tan. And then we have to do one more derivative. Yikes. So we're going to treat, in my mind, I see it like this is f, the first function. This is s, the second function. So first derivative second, Derivative of tangent is secant squared. So first derivative second is going to give us that. First derivative second plus derivative of first times the second. The derivative of the first is 4 secant to the 1 times the derivative of secant, which is secant times tangent times the second, which will give us the tan squared there. So gnarly product rule. Gross. We are choosing A to be 0 because that's super close. That's a known, we know the tangent of 0. So we're trying to pick a number that's close to the number that we're using as our approximation location. And we want to pick a value that the function can be evaluated at easily. So another choice we could pick, we know tangent of pi over 6 exactly. So you could pick pi over 6, but 0 is closer. Or negative pi over 6 you could pick, but 0 is still closer. Okay, now we evaluate the function and its derivatives at this center. So y of 0, tangent of 0 is 0. Y prime of 0, secant of 0 is 1. Y double prime of 0, oh, 0 again. Because tangent of 0 is 0. And then y triple prime of 0, that one is 0, that one is 1 times 2. So we can see here that the third order approximation is going to be the same as the second order approximation and the fourth order approximation because those coefficients are both going to be 0. Right? If second order approximation, if we went out here but that coefficient is 0, that means the second order term is disappearing.
Yeah.
It's going to become 0. So the third order approximation is going to be, did I say something wrong there though? The third order approximation is going to be the same as the fourth order approximation. Right? The fourth order approximation has a 0 right here.
I was gonna say the even are gonna be zeros.
The even ones are all going to be 0, so the second order approximation is the same as the first order. I think I said the third order is the same as the second and the fourth. I said that wrong. The second order, the third order is the same for the third and the fourth. The first order is the same for the first and the second, because there's not going to be an extra term when we go to this piece of 2.
So basically, if you start seeing that pattern, can you just skip the evens then?
Yeah.
So let's say you want us to go to 7.
And we know the evens are all 0. The only
These
problem
all
is
zeros.
you have to get to here, though, to get to here when you're differentiating.
Yeah, I know.
But-
You're gonna have to
but-
differentiate all the way down to 7, but then when you see the pattern, you can just skip.
Ixnay those values for
Yeah.
all of those evens. Yes, 100%. Okay, so we're going to go with a piece of 3. So piece of 3 of x, it's a function, starts with value. I'll write the zeros in here just to make sure. Plus slope. Come on. Plus slope. So hard. Not being able to write from an angle is such a drag. You've got to be like right on top of it. So value plus slope times shifted x. Well, there's no 0, so it's just 1 times x. Let's write that as just x then. So that. And then we go to the second order derivative, which is 0 divided by, if we're going to put it, 2 factorial times x squared, plus 2 divided by 3 factorial times x cubed. And here, let's go ahead and simplify it just because we have those 0 coefficients. This one is so easy to simplify, let's just do it. So there is our third order approximation, which is also would be the fourth order approximation, right? This would also be p sub 4, because if we went out to the fourth derivative, we would get 0, so p sub 3 and p sub 4 are the same. So if we want the value of this at negative 0.1, we are going to plug in negative 1/10 for these x's. And if we do negative 1/10 cubed, we're going to get negative 1 over 1,000. So then that is going to be whatever it is. I guess we're going to multiply this one by 300 over 300. So we're going to have negative 300 minus a 1, all divided by 3, 0, 0, 0. Is everyone tracking? Does that all look good?
Why is it 1/3 instead of 1 to 3 factorial?
I canceled the numerator 2.
Oh, okay.
So it's 2 over 6 right there, so that I reduced to 1/3. Multiply that by 300 over 300. So there is our approximation. And if they told us to use decimals, they would tell us how far to go. But now, they did ask us for absolute error, right?
Yeah.
So absolute error is always a positive number, but it's always positive. Let's come over to Desmos. Get rid of those. All right, so what was it? We were doing tangent of negative 1/10. So we have that. Then our approximation is negative 301 divided by 3,000. So the absolute error, I think it's self-explanatory. It's just the difference between the two. So if we do tangent minus 0.1 minus 30, whoops, I need to change the sign though. Because we're doing that, minus is plus. That is almost the absolute error. What do we have to do to make it the absolute error?
Multiply or not?
Yeah, we just take the absolute value.
Multiply by -1.
So if I just do this, whoop, make both those minuses, that is the absolute error.
1 million?
Yeah, that's pretty tiny. Tiny, tiny, tiny. So absolute error is just the difference in the value that you get minus the approximation. And then you take the absolute value. So that is our absolute error. And so obviously the goal is to have the error as close to 0 as possible when you're doing these types of things. The closer you can get to 0, the more accurate it is, which means the more money you can make.
And what are you trying to approximate?
We are approximating tangent of negative 1/10. You know, and obviously these first ones where you're learning approximations, you could just type tangent of negative 1/10 into your calculator, right? Right. So so the idea is that we start with ones that you can do, you know, in lots of different ways. But as you get to more and more complex things, finding these approximations gets more and more complex. You just want to get the concepts down though first, before getting to things that are wicked complex. Okay, so natural log of 1.05. Actually, I don't want to do that one because Declan had asked a question that I want to answer, and this will take more than 2 minutes. So he posted this. He kind of hid it in the questions up here. I didn't even see it because he put it in the third question blank, and he didn't rename it, so I didn't even see it there. Night before last. But it's a really good question. He and I talked about it earlier. So let's take a look at this one for a moment, because this one is interesting because we have a factorial thing and we are trying to figure out that quantity right there. We want to know, he has that backwards though, it should be greater than 10 to the 5th. So let's go through this one from scratch. So we want to know how many terms to have an error less than 10 to the negative 5. That's what we want. And so what we've been doing is saying, well, we want to figure out what the n value is to have a sub n or a sub k, doesn't matter what you call it. We want to have that less than 1 over k factorial. Oh, excuse me, less than 10 to the negative 5th. I was getting preoccupied by how fat that ink looked. So we want to know what the n value is to have this be less than 1 over 10 to the 5, less than 10 to the negative 5. That's what we want to know. So we want to figure out, okay, well, when is 1 over k? Ooh, I feel like I'm drawing with crayons.
Yeah.
It feels really
Clunky.
kind of fun. So if we want to know that, the only way to know that is to go to your calculator. All of our calculators have factorials, and there's no inverse factorial that you can use.
Also, if you're just using like phone calculator or whatever, you can just keep multiplying by the next consecutive term.
100%.
Something big enough instead of just trying to like guess and check.
Right, exactly.
Just start plugging.
So if we do something like 5 factorial, we get that, that's 120. You could then just multiply that by 6. I mean, here it's simple enough in this computer to do this, but, and 10 to the 5 is how much?
100,000?
So if we want to just get a look at that, oh my gosh, what is that?
What did you do?
10 to the, I don't have light over here.
Yeah.
Okay, so 100,000, so we're not there yet. So we go to 9.
And there.
9, okay, so 9 is the first integer that works. So this tells us that k has to be 9. So that is the first term that works. That tells us that a sub 9 is going to be smaller. So then we add up everything in front, but this started at 0. So we're going to add up a0 to a sub 8,
Which is 9.
9 terms. That make sense? All right, we'll stop there. Done with week 11.
4 more?
Why does it just feel so shy?